Good day, statisticians. Today we're going to be talking about combinations and transformations of random variables. There's really just going to be some really beautiful shortcut formulas that will help us deal with some otherwise slightly time-consuming kinds of questions. And what do we mean by that? Well, consider the spinner here. Say we have the spinner, and let's let x be the amount that you would win on a single spin of the spinner. Well, we could calculate some parameters of the theoretical results, and on average, you would win $5 per round, right? You either can win 0 or 20. The probability of winning 20 is 1/4, and 1/4 of 20 is 5, and 0 times 3/4 is 0, so clearly expected value is $5. And then we could figure out that the variance of the theoretical distribution and the standard deviation are these respective values as well too. And you could verify them either using the formulas that you've learned or by going to the calculator. But I'm just going to give you those as being the case for this particular spinner. You can just believe me, or you can verify it yourself. Go ahead, verify now. Yeah, it was right. Okay, so here's the real problem that brings us together. Let's imagine this. Let's imagine that we play this game twice. We played the game twice. What's the expected value and the standard deviation of our total winnings, right? What's our expected value and the standard deviation of our total winnings? All right, so let's calculate that. Now, what we're going to learn today is, again, there are some formulas that would make this problem very, very easy, but we don't know those formulas yet. So we're going to learn them today. But how would we do it if we didn't know the formulas? Well, if we play the game twice, we could come up with the PDF of that distribution, right? Where we could talk about, for instance, some total, right? And that total would simply be like what you won the first time plus what you won the second time. So I could call that like x1 plus x2. And we could see that there's, in fact, 3 possible totals that you could get. You could either win nothing, so sad, right? Either by spinning 0 the first time and 0 the second time, or the best case scenario is you could win like $40, where you got 20 and 20 again. Then there's that in between where maybe you got 0 and 20 or 20 and 0, in which case you won $20, right? So the probability, right, of this x1 plus x2, right, will be based on the spinner here. So what's the probability that you win 0? That would be like 3/4 times 3/4. That would be 9/16, right? What's the probability that you win 40? Well, that would be like 1/4 times 1/4, getting 20 twice, and that would be 1/16. And then from there, we can easily deduce that this guy must be 6/16, even without calculating the probability directly. And there's our probability distribution for the total. So now if I wanted to get the expected value in the standard deviation, I could just go ahead and plug this into my calculator. It would be one of the quickest ways, especially to get the standard deviation. And I did this earlier, and you could go put this distribution in your calculator. Hopefully you know how to do that. And we'll see that the expected value, right, of x1 plus x2 ends up being exactly $10, right? And the standard deviation ends up of x1 plus x2 ends up being $12.25 approximately, rounded off to that. So, all right, yay, that's nice. Well, let's reflect on that for a moment. Let's, in particular, the expected value of $10. Are we entirely surprised that the expected value of playing this game twice is $10? You shouldn't really be that surprised because, well, for playing the game once, the expected value is $5. So if you play twice, it would only make sense that you would expect to win double. So great. Fun fact, we didn't have to create this PDF and express it as a table or any of that garbage in order to answer this question. We could have, at least to get the expected value, all we'd have to do is double 5. Is it possible that we could have done the same thing for the standard deviation? Well, here we saw the standard deviation was $8.66, and now we see the standard deviation of playing twice is $12.25. There's not necessarily an easy, obvious way to show that how to go from this value, $8.66, to $12.25. It's not obvious. However, what is interesting is, what do you get if you square $12.25? What do you get if you square the standard deviation? In other words, you find the variance. Well, if you plug it in your calculator, you'll see that the variance comes out to being, and in fact, the variance is exactly, the variance of x1 plus x2 ends up coming out exactly to $150. Now you might say, $150. All right, that's nice. Why is that important? Do you notice something? and actually not $150. What am I trying to say? It's actually $150 squared, because this is, here we're talking about variance. Variance is in unit squared. So the variance isn't $150, it's $150 squared. But anyway, 150, that number, does that look familiar? Check it out. That just so happens to be double 75. Ah. Do you think that was by accident? It was not. It is absolutely the case. No, if the expected value got doubled to being 10, we'll see that, in fact, something else also gets doubled when it comes to the spread of the distribution. The variance got doubled. The variance goes from 75 to 150. So when you play the game twice, the variance gets doubled for accounting for those two plays. And so this leads to a beautiful set of formulas, right? For any two variables, x and y, it doesn't matter what they are, this is always the case. The expected value of x plus y, right, is always going to be equal to the expected value of x plus the expected value of y. That shouldn't come entirely shocking, right? We saw that when you played the game twice, you could just double the expected value, because that would mean like, oh, the first time you played, the expected value was 5, right? Let's do this. Let me get a different color. The first time you played, the expected value was 5. The second time you played, the expected value was still 5. And so the expected value of the sum of your two plays should be 10. That makes sense, right? Nothing too shocking there. This formula is very intuitive, and it's true for any two random variables, x and y. It doesn't really matter much about them all. You can always add the expected values to get the expected value of the sum. However, what if we're dealing with the variances? So here's going to be another set of formulas. Whenever you have two variables, x and y, that are independent, and this formula only holds if your two variables are independent, then what we'll say is that we can get the sum of the variance of the sum is going to come from the sum of the variances. The variance of x plus the variance of y, right? So we can't add standard deviations, but we can add variances, right? So to get the variance of the sum, you would add the variances. So that's very nice. That so say in turn I wanted to, my real goal was to know the standard deviation of x plus y. Well, the best way to get that is to start off by finding the variance and taking the square root. The standard deviation of x plus y will be the square root of the variance of x plus the variance of y. There we go. These formulas, right, are always true, right? The only caveat for the second set of formulas is that we have to assume x and y are independent. And when we're spinning a spinner, we can assume that. Whatever you spun the first time isn't going to change the probability of what you spin another time. So in this instance, to answer number one, like now that we know these formulas, instead of spending like 5 minutes sitting here fooling around, you could answer it almost instantaneously. You know that you play the game twice. You would just add sum your two variances, and you could get the variance of the sum. The variance is 150. Take the square root of that answer, and shazam, you'll get your correct standard deviation. So that's really, really nice. Now, let's take a step back, because as soon as we write down these formulas and things like that, students, in many years, I've had students object, right? As soon as I wrote down that the total is really x1 plus x2, students are like, well, couldn't I just simply write that as like 2x, right? That if you play the game twice, that's just like, well, we know from algebra 1 that x plus x is 2x, so couldn't I just do 2x? Well, the answer is, sadly, no. That, in fact, x1 plus x2 is not equal to 2x. It's simply not. Whoa, the lights went out. Let me fix that. There it goes. Not that I need the lights, but it's better with lights. But x1 plus x2 is not equal to 2x. Now, why? Why? Well, there's a couple ways I can justify that. What 2x simply would mean is that, well, if 2x means I spin the spinner once. I spin once, right? And in fact, I'll double the result of what I spin, right? So what does 2x mean in this context? 2x means that I only spin the spinner once, but I double the potential winnings that I have, right? And so if I double the potential winnings, my spinner is no longer 0 and 20. It's really like 0 and 40, because 0 times 2 is 0, and 20 times 2 is 40. So now that distribution, 2x, is not the same thing as two separate spins. This is like two spins, right? This is two spins altogether, and this is just one spin doubled. Now, What would be the parameters of 2x? Well, we could write the quick probability distribution, right? I could say, oh, 2x, right, has two possible values, either 0 or 40, right? And the probabilities of 2x, let me get that. The probabilities of 2x would be, well, still 3/4 and 1/4. And so we could find that the expected value of 2x ends up being 40 times a fourth, which is $10. Now that looked familiar to us, right? Remember, that was the same thing as the expected value of x1 plus x2. Remember, the expected value of x1 plus x2 was also $10. So there's no difference. That's not a difference. Well, what would be the standard deviation of this? Well, we could plug this in our calculator and we could verify it. But as it comes out, the standard deviation, you plug it in your calculator right now and check. You'll see that the standard deviation of 2x comes out to being, I believe, $17.32 approximately, right? Which, as you'll see, is in fact exactly double $8.66, right? And we talked about this earlier in our course, right? We talked about, in fact, we learned this fact earlier in our course, that 2x is really just a linear transformation. It takes all your values and makes them twice as far apart from each other, right? And so any measure of spread should base, any measure of spread in the same units will become twice as large because the data is twice as far apart because every value is multiplied by 2. Multiplying changed the spread by a multiple of 2. We learned this earlier in our course, right? And so we see the same thing here again when it comes to combining random variables. That 2x, right, the standard deviation of 2x is going to have double the standard deviation of x. But it's not the same thing as the standard deviation of x1 plus x2, right? It's because there you're going to add our variances, and there we got $12.25 and stuff like that. Okay, so very, very nice. Does that make sense? All right, so let's try a couple of additional practice questions on this same idea. Here I found the expected value of 2x. Here, let me get rid of all this guy. It's gone. So let's just do a couple problems here. Here we see the same formulas that I just told you on a nice slide, and let's do a couple problems. So here, let's imagine that we have two random variables, x and y, that are independent with these parameters. Let's find very quickly first the expected value of x plus y and the standard deviation of x plus y. All right, I'll do that really quick. When it comes to the expected value of x plus y, that'll be the same thing as the expected value of x plus the expected value of y. Oh, I just noticed I got cut off a little bit. Let me clear that off. The expected value of x plus y is equal to the expected value of x plus the expected value of y. Why am I writing that down? Almost don't need to. That should just be 5 plus 18, which would be 23. That was easy. All right, but what about the standard deviation of x plus y? To get the standard deviation of x plus y, then what I'll do is I'll take the square root of the variance of x plus y. Now, to get that, that'll be the square root of the variance of x. Let me write this here. The variance of x plus the variance of y. And so that'll just be the square root of, let's see, the variance of x is going to be 3 squared. So let me do 3 squared plus the variance of y, that'll be 7 squared. 3 squared plus 7 squared is the square root of 9 plus 49, which would be 58. Is that right? Am I mathing correctly in my head? I think I am. Which would be some number between 7 and 8. And I don't have a calculator in front of me, so I'll just leave it be. But it'll be something around like 7.5 or so. Something halfway, or close to halfway between 7 and 8 or so. Square root of 58. Simple enough. Is that good? All right, let's do another problem, right? Let's say, all right, let's actually, you know what? I don't want to do that problem. Let's kick it up a notch here. Let's say I was considering something like, let's find the expected value of, say, x plus 2y and the standard deviation of x plus 2y. All right, that's similar to what we just did. If I was to do this problem, I'll say the expected value of x plus 2y will equal the expected value of x plus the expected value of 2y. Okay, so we know what the expected value of x is. Expected value of x is 5. right here. Let me get a different color. 5, right? Boom. And the expected value of 2y, well, we know the expected value of 2y will be 2 times the expected value of y. So 2 times 18 is 36. Yeah, 18 times 2 is 36. Yeah. And then 5 plus 36 is 41. So the expected value of x plus 2y is 41. That's easy. Nothing too fancy there. Well, let's do the same thing with the standard deviation. What's the standard deviation of x plus 2y, right? Well, we know to get that, let's do the square root of the variance of x plus 2y, okay? And so that will equal the square root of the variance of x plus the variance of 2y. All right, with me? All right, so the variance of x, that's easy, right? We'll just do, that's the square root of, all right, the variance of x is just 3 squared, which is 9, right? Plus, now the variance of 2y. What is the variance of 2y? Well, remember that the standard deviation of 2y, right? The standard deviation of 2y will simply be 2 times the standard deviation of y, right? Because that's a linear transformation like we learned earlier in our course, early in the year. So that would mean the standard deviation, this will be 2 times 7 or 14. So when I go here, right, I'm going to say this is the standard deviation of 2y is 2 times 7, which is again 14. And that is what gets squared, right? It's not, it's 14 squared. So that means, right, the standard deviation of x plus 2y is going to be the square root, right? The square root of, again, 9 plus 14 squared. 14 squared, that's like 196. Is that right? I think so. Am I going crazy? Yeah, I think that's right. And then 9 plus 96 would be this. 196 would be what? I can't think today. 203. 203. Am I going crazy? I feel like I should take out my. I don't know why my brain is not working the way that I want it to right now. Here, you're probably yelling at your screen right now, like, "Oh, you're right. Oh, you're wrong. Why are you doubting yourself?" Like 14 times. Well, here, let's calculate. 14 times 14 is 196 plus 9, 205. Why did I say two? See, there you go. Why did I say 203? I knew. Part of me just was feeling crazy there, so I knew something wasn't right. You're like, wow, how are you a math teacher if you can't add 9 plus 196? I don't know what was going on with my brain right now. That's why I have a calculator sometimes to make me feel better about myself. And so the square root of 205 ends up being about 14.3. That was actually kind of embarrassing. I'm embarrassed that in the heat of the moment as I'm sitting here recording this, that for some reason I added 9 plus 196 and got 203. I'm slightly embarrassed. All right, let's just do one more example, shall we? Let's do one more example. Let's imagine it's different than, again, different. I chose not to do this example, but let's do one more example. Let's just do something simple. What if I said, what's the expected value of y plus, say, 20, right? Well, there's an easy way and a hard way. Let's do it the long, hard way. That would be the same thing as the expected value of y, right, plus the expected value of 20. Okay, well, what do you expect y to be? Well, we already know that we expect y to be 18, so that'll be 18, right? What do we expect 20 to be? That's kind of weird, because, we didn't give any parameters for 20, but 20 is just a number. 20 is a constant. So what do you expect 20 to be? I don't know about you, but I expect 20 to be 20. 20 is always 20, right? So yeah, the expected value of 20 is 20. So 18 plus 20, that would be, I'm not busting out a calculator this time, that's 38. There we go. Okay, so that's obvious, right? If you just add 20 to every value in your data set, then the mean would go up by exactly 20 from 18 to 38. Okay, so that's fine. Well, let's do the same thing now. Let's get the standard deviation. What would be the standard deviation of y plus 20? Well, let's do it the long way. That would be the same thing as the square root of the variance, right? So the variance of y plus 20. And, well, again, we're doing it the long way. That would be the same thing as the square root of the variance of y, right, plus the variance of 20. All right, so let's reflect for a second. What's the variance of y? Well, I know the variance of y. Oops, let me get the square root. That's the square root the variance of y, we know that y is 7, so 7 squared is 49. All right, and so what's the variance of 20? Well, how much does 20 typically vary from itself? This is kind of like saying, I'm thinking of a number, right? I'm thinking of a number in this set, right? And here's the set. The set is the number 20. All right, pick a number from 20 to 20. What are you going to guess? 20. If I ask another person, what will they guess? 20. If I ask another person, what will they guess? 20, right? What's the variance of 20? 0, right? So in fact, the standard deviation is 0. You're always, if I say you're picking the number 20 from the set that only includes 20, you're always going to get 20. That's going to have a standard deviation of 0. So in other words, the variance of a constant, anytime you have the variance of a constant, right? The variance of any constant is always going to be 0 because a constant will never vary from itself at all. And so as it turns out, the standard deviation of y plus 20 is just equal to the same thing as the standard deviation of y, which of course is 7. So there you go. All right, there was a couple examples. I hope this is helpful to you. Have a very beautiful day, and I will see you in class tomorrow, hopefully. And if I don't, then maybe I'll record another video. We shall see. Have a glorious day. And I'm trying to hit stop recording right now, and I'm doing it. See ya.